Hello everyone, welcome to this video lesson. Today in this post where we are talking about a topic called electric charges and fields, we would like to calculate electric field intensity of a system. Our system is in such a way that it is having 4 charges at the 4 corners of a square. All the charges are identical. Being a square, all the sides are also identical. Like this, we are having a square where all sides are equal, and at each corner, let us assume, we have kept identical charges, q, small q, all charges are positive. We want to calculate electric field intensity at any corner of the system. Say for example, at this corner I want to calculate. For the namesake, we can name this as something like A, B, C and D. I want to calculate electric field intensity or else electric resultant force because there is a charge at any one corner, say at the bottom corner. On this corner there will be force due to the charge at the corner D, as both are positive charges. On the charge at the corner C, charge at the D applies a repulsive force. Let me call that like F1. And on the charge on Q, the charge the corner charge B also applies a repulsive force because they are also similar charges. So let me call that like F2. Now I would like to calculate what is the magnitude of this F1. We can write as per the Coulomb's inverse square law, 1 by 4 pi epsilon naught. This is Q and this is also Q, Q square. Pi, this is the side A square. And it is very clear that even the magnitude of F2 is also the same because the charges are same and the distances are same. But if you notice, they are not in the same direction, rather they are perpendicular to each other. F1 is perpendicular to F2. So if I have to calculate the resultant of F1 and 2, I can use the parallelogram law of vectors, root of F1 square, F2 square, 2 F1, F2 and cos 90, but that cos 90 term is 0. So the third term becomes 0. So the value is nothing but equal to root 2 times of F1. I can write what is the value of that F12 is nothing but root 2 times of either F1 or F2, whose value is 1 by 4 pi epsilon naught Q square by R square or A square, who is the side. I am also interested in identifying the direction of it. As F1 and F2 are equal, their resultant will be exactly in between, making an angle 45 with either F1 or else F2. That means it is exactly in between. Now I want to calculate what is F3 is. On the charge at the corner C, the charge of the corner A also applies a force. What kind of force? Let us try to identify. Both are positive charges. So this is the direction of F3 because that is a repulsive force. If this is A and this is A, this distance becomes automatically root 2 times of A. So I can write a formula. F3 is nothing but equal to 1 by 4 pi epsilon naught. Both are Q's, Q and Q. By this distance is nothing but equal to root 2 times of A whole square. So value of the F3 is 1 by 4 pi epsilon naught Q square by 2A square. It is also clear if you look at the diagram, the direction of the F3 is parallel to that of the resultant of F1 and 2. So if I have to calculate the resultant of all forces, I have to add these two forces. I can directly add like a scalar since the angle between them is equal to 0. When the resultant is, when the two vectors are parallel, F resultant is nothing but equal to sum of that forces. So if I have to add, that is what I have to calculate in this problem. F resultant is, though we have named it like intensity, we are actually calculating the resultant force on the system because there is a charge there. So, we are actually calculating the resultant force. So, F resultant is, what is F12 we know, what is F3 we know. For both of them what is in common is 1 by 4 pi epsilon naught q square by a square. F12 has a root 2, F3 has a 1 by 2 extra. This much is the resultant force, that what we want to calculate is the force acting on the any one corner, whatever may be the corner is. Now, I would like to extend this discussion a little further. What is the extension that I want to calculate? What I want to do is, I want to keep the entire system of these 4 charges in equilibrium. To keep the system in equilibrium, so what is my question is, to keep the system in equilibrium, to keep the system in equilibrium, what charge has to be placed? What charge has to be placed at the cross section of the diagonals? At the cross section of the 2 diagonals. Say, this is the cross section of the diagonals. Here I have to keep a charge. Let me keep a charge capital Q. By keeping that Q, I want to say is the resultant force acting on each of the charge has to be equal to 0. First of all, if I have kept a positive charge, say for example, if I have kept a positive charge, if I have kept a positive charge or a negative charge at the center, that charge can be definitely in equilibrium because the charges at the other 2 corners applies equal force on it but in the opposite direction. Therefore, capital Q can be in any way in equilibrium. But if I have kept a positive Q, this positive Q on this positive charge also applies a repulsion. Therefore, this small q cannot be in equilibrium. So, to keep any of the small q in equilibrium, we have no choice other than keeping a minus q, negative charge at the cross section of the diagonals. On this negative charge, this q applies a force of attraction. This q also applies a force of attraction, both of them cancels. So, that negative charge will be anyway in equilibrium. Now, if I have kept the negative charge, on this small charge, this negative charge applies a force of attraction. Then, as these 2 forces are in the opposite direction, I can put a condition. If that force, F4, whatever I am talking, is equal to resultant of F1 and 2 and 3. As they are already opposite in direction, each charge, and hence the system can be in equilibrium. Each charge and the system can be in equilibrium. So, the condition that what we need to know is, we shall keep a charge who is a negative charge. How much is that? Let us try to calculate by writing the condition. F4 is equal to 1 by 4 pi epsilon naught minus q between this and this, and small q by the distance. As the total distance is root 2a from here to here, as this is half of it, the distance between these two is nothing but equal to root 2a by 2. That is nothing but equal to a by root 2. So, a by root 2 whole square equal to resultant force. We have already calculated that, 1 by 4 pi epsilon naught q square by a square of root 2 plus 1 by 2. So, 1 by 4 pi epsilon naught can be gets cancelled, a square also gets cancels, one charge anyway gets cancels. What is remaining is minus q by 1 by root 2 whole square equal to q root 2 plus 1 by 2. So, 1 by root 2 whole square is 1 by 2, that will become into 2 minus 2q equal to q by 2 to 2 plus 1 by 2. So, the charge that we have to keep at the cross section of the diagonals to keep the entire system in equilibrium is a negative charge having a magnitude of 2 to 2 plus 1 by 2 by 2. If you keep this much of the charge, entire system will be in equilibrium. Thank you for watching. Please sign up, and you can also see lots of other problems in this academy, venkatacademy.com. Thank you.